Okay, we're going to talk a little bit about some of the different techniques that we have for doing implicit measurements of the brain. So, I guess we'll start here, right? So the first one we have is a single unit. And a single unit is basically measuring activation in a single neuron, right? A single neuron in the brain. And so a single cell is going to have a electrode that's about 1/10,000th of a millimeter, and it's capable of measuring changes of 1/1,000,000th of a volt, right? In its changes in electrical activity, right? So when the neuron releases neurotransmitters, it crosses a chemical potential that then creates an electrical signal. It's very faint, very small, right, because it's a single cell, but then a single unit recording is basically something that's going to look at single neurons. And so some of our earliest experiments were done, which shows that, like, in our field of vision, we actually see pixels, right? So we have a single neuron that's going to be tied to a single nerve ending in our eye, and so when our eye sees a certain light or certain color, it's going to activate a single neuron. And if you turn your head just slightly, and now your field of vision is altered, well, now it's going to activate a different set of neurons. So we really do see these pixels, and then there's additional processing in our brain that's going to take those pixels and make sense of them into contours and then to shapes, then to other signals, and we have this layer of processing. In fact, probably the largest function, the largest area of our brain is dedicated towards visual processing. And we're very visually oriented people for doing that. It's that same model that has led the way to neural networks in computer science, where the idea is, instead of just looking at your dependent variable as a function of all these other independent variables, hey, if we can identify, like, essentially pixels and then make a layer of sense like contours and then shapes and then other, like, objects, and if we can have this layered approach, then maybe we can actually improve the performance of making sense of data and delivering insights. And that all came out of work that was done in single unit measurement devices more than like 5 or 6 decades ago. The next one is event-related potential. Event-related potential, ERP is what it's called. And so event-related potential is that there is some sort of stimulus in the environment, and then that creates some sort of electromagnetic field that can be then measured, not necessarily with a single unit, but in any number of systems, right? Like EEG is something that basically has little electrodes, and it's looking for electrical signals that you would have. So it's those event-related potentials that kind of drive EEGs. There is positron emission tomography. Or a PET scan. Now, positron emission tomography basically has some sort of radioactive substance, and then it's measuring the release of positrons from the radioactive substance that's in your brain. So that would be another method. There is functional magnetic resonance imaging, fMRI. And what that's doing is it's looking at, so when neurochemicals are released in the brain, then oxygenated blood will come and resupply those chemicals to those regions of the brain. And so what we're detecting is the electromagnetic properties of the blood that's resupplying the brain. So it's not going to detect exactly when the when the stimulus occurred. It'll detect that resupply of that. So that is what we call a I'll make a special note of it here, blood oxygen level dependent, right? So that's a bold signal, blood oxygen level dependent, because it's looking at the blood, the resupply of the blood. There's another one, functional near infrared spectroscopy, or FNIRS. And this works very much the same as the fMRI signal. However, so it's also using a bold signal, but it is optical instead of magnetic, right? So it's basically, if you've ever gone into a doctor's office and they put the little alligator clip on your finger to measure your oxygen level, right? Well, what it's doing is your tissue, oxygenated tissue absorbs light at different wavelengths than deoxygenated tissue. So when they can shine light at a couple different frequencies onto tissue, right, they can then look at the difference and measure the amount of oxygenation that's in that tissue. And so we use that kind of technology to measure brain activity of a bold signal in the near infrared spectroscopy, right? So that's FNIRS. We have event-related fMRI, right? And that's EFMRI. And that's a combination of the event-related potential, so some sort of stimulus, and then measuring the fMRI response to repeated signals. So with the event-related potential and the event-related fMRI, what you're doing is you're doing repeated stimulus on, off, so that you can actually measure that pattern of neural reaction to that. Now, we don't really do that with the FNIRS because there is it doesn't quite have the resolution, the detail to actually get at those functions, and there's also a time latency that any bold signal has, because you're measuring the resupply of blood. There is magnetoencephalography, right? And that's MEG. And what this does is it measures magnetic fields in your brain, right? So it's looking, again, very similar to the functional magnetic resonance imaging fMRI, but it is actually not measuring the magnetic properties of the bold signal. It's trying to measure actual the actual electrical fields that are created from the release of neurotransmitters. We have transcranial magnetic stimulation, TMS. And this is where they take little coils and they create little magnetic fields on areas of your brain, which creates temporary lesions, which basically inhibits brain function in those areas. So they say, hey, if they stop certain activity in certain regions of the brain, does that affect you, right? So that's TMS. They also have repetitive TMS. Has this nice little RTMS, and it's just what it might seem, right? Is they're going to do repeated bursts on these little electrical coils on your brain that creates these lesions, just to see how that affects your behavior. And so these kind of describe the general approaches that we have for looking at brain activity. Now, what I'm going to do is there's two concerns that we have when we look at brain activity, right? We are concerned about the time, right, or latency. And we're interested in spatial resolution. Okay, spatial resolution. So I'm going to create a little scale here. We'll make this -4, -3, -2, -1, 0, 1, 2, 3, 4. And this is going to be on a log millimeter scale, right? So log millimeter scale. And what we're talking about is this is kind of like brain. I'm going to use a different color so you can see this a little better. So we have kind of like at the level of the brain, right? Big brain regions. Maybe a brain map here. We have a synapse, right? That's between neurons. We have a dendrite, neuron level, neuron. This is maybe a layer, right? Just to give you some perspective. And then if I go down here and we start with like -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, right? And this will be on the scale of log seconds. So just to give you some perspective, this would be like a millisecond. This would be a second. This would be a minute, an hour. This would be like a day, right? Day latency to process. So what you have is the single cell is going to be something along here where this is the time latency and the spatial resolution that you have from a single unit device. Single unit. If we're then going to look at the event-related potential, we're going to look at somewhere right around here, right? So this is going to be for both an MEG and ERP. So any kind of electronic, right? So when you're looking at the magnetic properties here or the event-related potential, these electrical signals of actual neurons firing is going to have very, very quick latency, right? Below the level of second, around the millisecond to second level. And it has not as good spatial resolution as the single unit, but it can still give you areas, general areas of the brain that are becoming kind of active. If we're going to go to fMRI, right? fMRI is same latency as that. In some cases, you can get a little bit better, but you're going to be not as fast, right? Because you have this bold second, bold signal. So you're going to be operating here if you're in the area of any kind of fMRI. Now, FNIRS, right, doesn't have the same spatial resolution, right? It's just the technology has not caught up yet. So for FNIRS, you're going to be a much lower spatial resolution up here. What are we missing? The PET, positron emission tomography, is also going to have worse latency when you're measuring like the radioactive properties. And so it's going to kind of overlap here for PET. And just by contrast, the one that is worse would be, somewhere out here is where we're talking about lesions. Lesions. Right, so when you have a brain damage type area. The other one I think we're missing is TMS, gives you area in here. And then there are some multi-unit methods, right, where you use some sort of single unit combined with some of these others to create a multi-unit measure. Okay, so it's important to say that depending on the system that you're using, you're going to have changes in latency for time and also the resolution of where you're going to get. For our purposes in our course, what we're assuming is that you need to be a little bit more portable. You need to be able to go out and do field work. And so we're going to focus our attention on FNIRS, which you see has the worst spatial resolution of any of these technologies, not particularly great time latency, but it is a fraction of the cost of these other ones. So just to give you an example, an fMRI system is probably going to be $1 million to set up into a lab, and you have to go into a large room so that it can actually function. Whereas the FNIR system, I can have an FNIR system that's about the size of this little book here, and it's probably on order of under $50,000 for such a device. So that's what we're going to kind of focus our attention on, and then we're going to supplement that with other biophysical measures. Okay, there are some limitations that I think are important to address, right? So if we're going to talk about some limitations for these methods, right? So the first one is over-interpret findings. Okay, so a lot of times there's assumptions that there's like a one-to-one mapping of areas in the brain. For example, people are exposed to some sort of fear condition or fear stimulus. There's activation in the amygdala, and so they say, well, hey, look, the amygdala must be the center for fear response in the brain. Well, further studies then say, you know what, the amygdala is involved in almost all emotional reactions, and it's maybe the emotion center, not the fear center. So sometimes when you have limited studies and you haven't done enough of them, we can overinterpret findings. And we're probably right on the verge for some of the material we're discussing in this class, where there's getting to be a dozen or more, dozen to 20 or so studies in each of these areas we're going to be discussing. So it kind of begins to create a sense that there's something there. But I'm going to give you some example data where maybe those give you pause for thought. So overinterpreting findings is the first limitation that we have in a lot of neuro studies. The second one is reverse inference. And this is an important concept you really need to know if you're going to call yourself a neuroscientist in any way. And reverse inference is, like just to pick up on the amygdala response, right, is you've been exposed to a fear condition, there's activation in the amygdala. Reverse inference would be, hey, I see activation in the amygdala, the person must be afraid, right? That's called reverse inference. And you can't do that with neural studies because of the example I said, where, well, what if there's some other emotional response that's activating the amygdala, right? So a lot of times brain regions are involved in multiple processing. And so if you don't have a hypothesis, if you don't have some sort of other broader theory that's supported by multiple studies in the field, you've got to be really, really careful about how you're interpreting that data. Right, that's why the lit review in this course is so important. That's why it's important to become familiar with other studies that people have done. A lot of the studies are underpowered. So that's getting at your false alarm rate, right? So a lot of studies in neuroscience are done with like less than 20 people. So there's very, very few examples, and so that kind of means that it doesn't have enough power to really assert those findings without a high probability of false alarm. So that gets into, there's oftentimes a high false positive rate. And the problem you have with the false positive rate is there's vast amounts of data that you're going to collect. And you'll begin to see this when we actually are doing data analysis. And so there's so much data that it's very easy for there to be some sort of signal that you want to attribute some sort of claim to, and that can lead to higher false positives than you have in typical studies. So the other limitations is our studies are associated, association and correlation. So what does that mean? Well, there's always activity in your brain, right? The idea of there being no electrical impulses, no firing in your brain is, that's just not what happens, right? Our brain is always active, it's always firing. So what we're looking at is we're looking at relative changes. And so what we do is when we have a stimulus or when we have some sort of exposure to something, right, we're then looking at a corresponding change in activity in the brain. It's not like the brain is like there's an area of the brain that's completely dormant and silent. We get exposed to a stimulus and then it fires. No, your brain's firing. It just might fire a little more or a little less under certain stimuli, and that's what you're detecting. So those are inherently correlational, right? So we're looking at correlational patterns. It's very hard to attribute cause and effect to a lot of these studies. I mean, we will to some of them, but it's very difficult. Brain activity, right? I'm just going to call this one out. Brain activity adds roughly 5%. So when you're looking at changes in brain activity as a result of stimulus, we're really talking about maybe a 5% change in brain activity as a result of some sort of stimulus from what's going on normally. And so that means that the signal to noise ratio is very, very low, and it can be very difficult to measure. There is an issue of ecological validity. Ecological validity. So, you know, you may have been exposed to the Hawthorne effect, right? So that's the situation where if people know that they're being studied, their behavior changes because they're being observed or they're being watched, they're being studied. So this gets into this issue of ecological validity, whereas if you're in a laboratory, is that really the same kind of situation, the same kind of findings you would have out in the real world? And we generally think no, right? There's some sort of issue with that. So this issue of systems, right? Well, it really depends. If you have a single unit recording device where you have an electrode in your brain, right, that is going to be not the same situation as when you're out in the world doing whatever you're doing. When you're looking at something that's very mechanical, like your visual field and which neuron is firing for which pixel in your visual field, right, that might be appropriate. But if you're looking at how you respond to emotional stimulus, right, or how you feel fear, for example, that may not be the best tool because the conditions of having an electrode in your brain are going to be very different than if you're just out in normal society. One of the advantages of FNIRS is it has better ecological validity because of its portability. You can actually move around with it. It doesn't have great spatial resolution, but it's kind of robust to things like movement, activity. So there's even like an FNIRS Sport where you can do physical activity, you can run and still measure brain activity. Versus an fMRI where you're in some big donut-looking thing. You can Google fMRI and see what one of those looks like, but you're on a little bed, you're put in one area. If you're claustrophobic, that can be really horrible, right? So each of these things have some trade-offs between the spatial resolution, the time and the latency, and the ecological validity that you're going to have. The neural imaging illusion. Neuroimaging illusion. I didn't make this up. This is a real thing, and there have been a couple studies finding that if you put a picture of a colorful brain with activity lit up, right, in just about any scientific paper, it's believed more, right? People are gonna trust your findings more. They're gonna think that it's more academic, it's more scientific, right? And that's called the neuroimaging illusion. So even if the findings don't tell you anything, I think there was a famous one where they found that chocolate, for chocoholics, right, they had a greater release of dopamine, right, so in the reward circuit of the brain was active when they were eating chocolate. And so really, that was published at The Guardian in a UK magazine, was going around about how brilliant this scientific work was. But all it really told you was chocoholics like chocolate, right? So it wasn't really that awesome of a finding. It was just saying, hey, you like chocolate, this area of your brain that's associated with rewards are activated. That's all it was saying. But because it was involved some neural imaging and some pictures of the brain, it got a lot more attention. So the last area that I want to bring up, which is not particularly related to this, is age, right? So it kind of falls in this area, but when we're looking at our cognitive development as we age, right, different areas of our brain develop at different times. So the brain is not fully developed until about 24, 25 years old, right? Which is, and actually the funny thing is the last area of your brain to develop is the area that kind of connects risk assessment with decision making, which is why adolescents can sometimes make foolish decisions, right? But aside from risk and judgment, one of the other areas that's very important is this concept called theory of mind. And so theory of mind is classically described as it usually occurs at about 4 or 5 years old. If you see a dollhouse, right, and have you ever seen the dollhouse where, the one side of the dollhouse is the front of the house, the inside of the dollhouse, you can kind of like see the rooms and the furniture or whatever. So if a kid is on the outside facing side of the dollhouse and an adult or another kid is on the other side, that kid on the front can't understand that your perception of what's in the dollhouse is different than his, right? Maybe a better example would be a small child can cover their eyes and now they can't see you, so their assumption is you can no longer see them, right? And they're hiding from you, right? And we kind of laugh and chuckle about that. Well, that is theory of mind. It's basically the point at which you can understand that other people have a different perspective of the world than you yourself do, right? And so then theory of mind is important because it's a key step in understanding social psychology, that other people are going to perceive your actions and your intent possibly differently than you perceive them yourself. And so now we're going to begin to pay attention to social cues and social norms, and it's kind of the foundation of social psychology. So that area of the brain becomes active in kind of mentalizing, which is in the medial prefrontal cortex, right here in your forehead, very measurable, very accessible. But the point is when you start looking at younger children that haven't necessarily developed that type of brain function or those pathways yet, then you're not going to see the same response as you will with older adults. And so I'd use that as an example, one, because it's a key area for influence and persuasion that we'll be discussing later. But the other thing is that age is another factor that is going to affect your brain activity and how we measure.